Okay. Hi, everyone. My name is Amit. I guess most of you know me, but just for the sake of completeness, I can say my name. Today, I'm going to be talking a little bit about private linear regression and some of the more practical aspects that I've been working on this summer. So I want to start by introducing the problem in sort of informal way and just the general justifications for why we should care about linear regression in private context. But even before that, I do that, I want to talk a little bit about the core message of the talk that I'll be giving today that I'll support kind of theoretically and empirically later on over the next half an hour or so. And this message is basically that under minimal assumptions, where I'm going to suitably talk about what minimal assumptions means later on, DP-SGD is going to perform well for private linear regression. It's going to be provably private in a floating point sense, which is really what we care about in the context of the OpenDP. But to return to a more standard introduction away from this core message, although I think it's helpful to keep this in mind for the rest of the talk. I think we all know why linear regression is important. I don't think this needs a huge amount of separate exposition, but just as a brief reminder, linear regression itself is a very useful, arguably canonical statistical procedure that's pretty useful in of itself. It's useful and really central to downstream statistical inference. So if I want to do something like generate confidence intervals for some predictions or any other statistic, I really need to be able to do linear regression. And linear regression is also used as a building block for more complex algorithms. For example, if I have some sort of a mass representation learning model and I want to do classification or regression in high dimension, linear regression is like the de facto tool for doing this kind of thing. So linear regression is a natural object of study for statistical learning, and I think is something that we should care about. Because we're OpenDP, the next question I'm going to ask is how we can achieve linear regression privately. The way to do this is broadly via private algorithms. And during this talk, I'm going to focus on these two classes of private linear regression algorithms, namely iterative and one-shot. To talk about one-shot algorithms first, we're going to map directly from data and some labels to an estimate. And we're going to do this at a high level by adding noise to the outputs of some immediate procedure. The other class of algorithms that I'm going to talk about are iterative. That is, we're going to make incremental solution progress. We'll add noise, and we'll keep doing this until we converge to something that we believe is a good solution that's close to what we think that the round truth solution of the regression problem is. So currently, in terms of what OpenDP has in the library, just to kind of set the stage for why I think implementing this is particularly important in the library, we actually only have a single private regression algorithm. This regression is called tailsen, which is strictly limited to 1D. So while tailsen internally is actually a pretty cool algorithm, and I think it's pretty nice, I think this limits the usability of OpenDP for practitioners and data scientists, just because doing something as simple as even low dimensional, where the dimension is something like the low dozens or something, is not currently possible with the library. And one can imagine that linear modeling is a pretty standard part of the data scientist toolkit in this day and age. So given all of this, I guess the first thing that I want to talk about more technically is what properties we should ask a good linear regression algorithm to have. I'm first going to talk about the privacy or properties related to privacy that we believe one of these algorithms should have. So in particular, I've got these two ideas that I want to make sure we keep in mind for the rest of the talk. Firstly, any algorithm that we implement in the library, we want its privacy analysis to be as close to optimal as possible. We don't want to be leaving stuff on the table, and for an algorithm that we implement to have much, let's say, better privacy loss in real life, then we might actually be able to show that it is. So we really want the privacy guarantees that for algorithms that we implement to be near optimal. Secondly, this is really like a necessary condition for as a necessary condition for actually being differentially private on finite precision machines. Our algorithms should be friendly to being made floating point safe. I stress this as a critical point because idealized numerics is not realistic. We know that there are work by some folks in this room, wherein floating point machines have significantly higher sensitivity and privacy loss than they would on idealized numeric under the assumption of idealized numerics. So this is actually a very important assumption and something that I'll talk about a lot. And outside of these privacy-related desiderata, one other thing we want is our utility guarantees to be accurate under minimal assumptions in the data. I mentioned this before, but I think the example that I want you guys to keep in mind for the rest of this talk will be something like data boundedness, which is typically reinforced via a procedure called clipping, wherein we take our data, we scale it down to some maximum norm or something like that. Clipping naturally is known to introduce bias in estimation processes. If we take a look at the image on the right, we can see that by taking this data distribution, which is uniform over an ellipsoid, and projecting it into a norm ball, because we don't have any a priori information on the size of this thing, we actually bias and change the data distribution a lot. And this can cause severe bias in statistical estimation tasks. And as we show later in this talk, can actually lead to pretty bad utility for fairly wide classes of private linear regression algorithms. So really, we want accuracy under like almost no conditions on the data, especially something like data boundedness. So given all of this, as a general setting for the problem we'll be talking about today, it's kind of unclear what private linear regression algorithms have this property of near optimality. So we want the analyses to be about as good as they can get. We don't know what algorithms extend to floating point safe implementations, and we don't really know what algorithms rely on these strong assumptions for practical utility. So my work this summer has broadly focused on understanding the trade-offs of various private linear regression algorithms with this lens of wanting to implement them in OpenDP as the, I guess, like ideal outcome for mobile. So to talk a little bit more specifically about the algorithms that we'll focus on today, we'll get in some experiments and also some theoretical analyses. I first want to set the problem in a more formal sense. So we'll consider data where these xi's are, I'll call them covariates typically, but these xi's live in some Euclidean space with response variables y sub I. We'll have n of these pairs. And for the sake of defining some averages, I'll say that these things are drawn from the distribution, but this won't really be relevant for the rest of the talk. We'll consider the best regression parameter given by some base truth, W star, minimizing essentially the average loss over a new draw from this implicit distribution. And we're interested in evaluating private algorithms, I guess, abstracted away via A of D, so some function acting on the data, randomized function, of course, that are going to approximately minimize something like the gap between the expected average loss over covariates drawn from this distribution compared to the best possible given by this W star. So to talk a little bit more about boundedness, we say that an algorithm is going to require bounded data if the accuracy guarantee of our algorithm, or the utility guarantee, and if you want to translate it into privacy guarantee, also that, is going to rely, if it relies on an access to a number R that upper bounds something like either the joint normal or the joint norm of both the covariate and its response variable, or just the covariate itself. And we'll say that an algorithm is going to require access to a bounded parameter if we also require access to a number, something like C, that upper bounds the norm of this W star. We're going to typically enforce these bounds via clipping, which is the procedure I mentioned earlier that may or may not introduce process, that may or may not introduce bias, but typically introduces bias. And to talk more about the algorithms we'll be looking at today, I think we all know what ordinary least squares is. As an analog of this, my work this summer has investigated AdaSSP, which attempts to basically privately release something that looks like this ordinary least square solution by perturbing this X transpose X term, privately releasing this X transpose Y term, and privately releasing something that looks like a regularization term, or more technically, a lower bound on the minimum singular value, sigma hat min. And we'll then release this, which is essentially a private version of this ordinary least square solution. Crucially, AdaSSP will require bounded data. There's no clear way to do AdaSSP without this assumption. And this is going to be important for the rest of the talk because we'll see that this assumption causes a lot of bias in certain statistical estimation tasks. As for iterative private regression algorithms, We'll look at some minima, basically algorithms that use something like stochastic gradient descent to iteratively minimize a tractable objective over data points that we know by, again, taking these initial solution steps, adding the noise, and iteratively doing this until we approximately converge to substationary distribution. The two algorithms we'll be looking at today are DP-SGD, which is going to make each of these gradient steps provide per step or per example clipping, take a gradient step and privately release each iterate via a technique called composition. Importantly, DP-SGD requires no assumptions on boundedness, and this is important. Noisy-SGD, which is a fairly similar algorithm, but crucially doesn't clip and privately release every iterate, but in fact only the last iterate, has guarantees that degrade with this bounded data assumption and with the bounded parameter assumption that I mentioned earlier. It's unclear whether this last iterate norm is automatically better than an analysis via composition. So having formally defined all these things, I want to state again the main goal of the work that I've done this summer and the rest of the talk, which will be to determine which of AdaSSP, DP-SGD, and Noisy-SGD, now well defined, have firstly near optimal privacy analyses, 2, extend to floating point safe implementations, and 3, don't rely on strong assumptions for practical utility. And to sort of sketch how the rest of this talk is going to go, just if it helps everyone keep it in mind, we'll show that for meaningful regimes, this final iterate bound the Noisy-SGD gives you over composition is actually not that helpful. And the privacy analysis of Noisy-SGD is actually only going to improve slightly over the composition analysis of DP-SGD. This is important because the implementation of Noisy-SGD in terms of the floating point privacy safety is going to be a lot harder. So it's unclear if that actually provides any benefits given the existence of point 1. Secondly, we want to show, or we'll show that DP-SGD can extend to a floating point safe implementation in a fairly natural way based on the numerical primitives that it requires. And there are some non-trivial gaps for both AdaSSP and Noisy-SGD that make them harder to implement in practice. And finally, we'll show that when data is bounded, all of these algorithms are going to have reasonable performance. When the data is not, and the assumptions of bounded parameter norm actually do introduce a lot of bias in the estimation process, DP-SGD will have the best performance by times orders of yeah. So to talk more about this first point and this last iterate analysis, I want to remark a little bit more carefully about what composition is. So composition via DP-SGD basically takes this perspective that we've released each of these iterates, whereas this last iterate analysis, through a much more careful analysis of each of these intermediate maps, which are something like gradient steps, is only going to consider and compute the privacy loss of the final step. Intuitively, what this says is that composition is going to compensate for more privacy loss than is actually necessary in the estimation process, because typically we only actually care about this final iterate. So in principle, this last iterate idea is going to lead to a less privacy loss. And one nice property about this is that as we take arbitrarily many optimization steps, the privacy loss of last iterate is actually going to converge.
In progress.
If you take a look at this graph on the right, wherein this, I guess this graph does converge if you were to put the number of iterations like logarithmically and pick some huge number. So the question we're asking here is whether this is actually useful. Like, is there a reason that we want to take this many steps and actually incur this kind of huge benefit? The answer, as we show, is typically not. Let kappa denote a constant that depends on the optimization problem, this tractable optimization problem that we're solving. This is actually the condition number of the optimization problem defined by alpha W. And known results basically show that Noisy-SGD is going to converge in about a number of iterations that's linear in the condition number. So running after this point for some technical reasons that are maybe outside of the scope of this talk doesn't actually incur any additional utility. It's possible to show, therefore, that the privacy loss that's incurred after about a linear number of iterations of the condition number is actually constant. The ratio between these two numbers is constant, which implies that this gap, the gap that we get between composition and this last iterate analysis, is actually fairly small. Just to sort of talk about this more illustratively, in terms of this graph, right? it's possible to show that up until a certain point that's characterized by the condition number, we continue gaining utility. So it's important to keep running. But up until this point, the analysis of both composition and last iterate analysis are actually quite similar, in fact, provably tight by the result that I had on the last slide. After this point, composition and the last iterate bound diverge significantly. So as the number of iterations goes off into infinity, composition will in fact have infinite privacy loss. But this bound actually doesn't matter because we're not gaining anything in terms of running the algorithm in terms of utility. So we have no reason to continue running, therefore we should stop here, meaning that we have no reason to deal with the huge back and forth provided by the last iterate bound. The second result, or the second idea that I want to talk about.
Can I ask a question now? And then I can go back to stuff. So presumably, so what you're plotting here is for the blue is that the known privacy amplification by iteration upper bound on privacy loss?
That is correct.
So these are both like we're comparing two upper bounds to each other, and they're still could conceivably be a tighter analysis for one or the other in terms of for linear regression or something. Or
I think so. This last iterate bound is actually exactly tight for quadratic problems.
Oh,
and linear regression, I guess if you have like a lower bound on the minimum eigenvalue, then you get that. So this is about tight.
great. And then is it like the takeaway message is the benefit of privacy amplification by iteration is kind of if you overshoot on your number of iterations, you don't know how many you're going to need to converge, then this is going to just like ensure you aren't paying penalty for those extra iterations somehow.
Something like that. I think one other point that I don't talk about explicitly here that should be mentioned is that if you're able to do accounting via amplification by iteration, you need access to essentially the same quantities that would allow you to characterize this condition number. So
I see. It's some dependence on kappa or something
exactly
in there. Got it.
So if you know enough information about your optimization problem to be able to do amplification by iteration at all, then you'd be better off just stopping early because you know where you have to stop.
Great. Thanks.
Does it inform how early stopping should be done to avoid this in the other speak and the other?
In DP-SGD, I guess there are for technical reasons that might be out of the scope of this talk. There's the fact that DP-SGD clips makes it harder to figure out like an optimal stopping time. But in terms of this composition versus last iterate analysis for Noisy-SGD, I guess like, yeah, at that point you can say like, at that point that's tightly characterized by the condition number. That's about as many iterations as you need. Yeah. So the next part I want to talk about, which is maybe a little less mathematical, is floating point safety of these three algorithms. So as I mentioned, there are a few papers, one by Ilya Mironov and another one by two folks in this room and some other collaborators, I guess. Floating point errors can lead to substantial privacy leakage, as an example, via underestimation of sensitivity, right? If we don't use some sort of like specific routes to avoid introducing this additional sensitivity in calculations. So one natural question to ask, given this existing result we've already shown, is to figure out whether DP-SGD, Noisy-SGD, and AdaSSP can each be implemented in an FP-safe manner. So I'll first talk about DP-SGD. And to sort of step back and to not talk super specifically about each of these components, it's not hard to see that DP-SGD actually relies on a number of fairly well-known and fairly simple components that allow us that we all know routes to get to floating point safety. For example, these gradient calculations actually don't matter because we're not summing across adjacent points. This clipping step is fairly trivial to make floating point safe. The sum function is also fairly easy to make floating point safe. I think this is actually discussed and covered in previous work. The only major or possibly non-trivial aspects to this are these make Poisson subsample Gaussian step floating point safe, but this is also fairly easy to do in practice, and it's something that we're currently working on an implementation for. So there are I want to stress that there are known routes for making most of this workable, and it doesn't require a huge amount of additional engineering. In terms of Noisy-SGD, this is actually not true. So for reasons that I felt it was best to immediately leave out of this talk, applying this kind of a less iterative analysis requires two steps that are sort of difficult to implement within primitives that already exist in the OpenDP library, or requires significant additional effort to implement in the OpenDP library. These gradients and summing calculations are all known. We know how to do these things in a floating point safe way, but we specifically need to first solve a derived optimization problem. It's a convex quadratic problem if it matters. It's unclear how to solve this problem in a floating point safe manner. Furthermore, composing these guarantees actually requires a fully adaptive numerical accountant that is floating point safe. OpenDP doesn't have this. It's unclear to me that there are known ways to make a numerical accountant floating point safe. So achieving a floating point safe Noisy-SGD is pretty hard, and it's unclear how to do it without a significant amount of engineering effort. Finally, in terms of floating point safe SSP, AdaSSP, we actually know how to do most of this. The only non-trivial step is the release of this singular value parameter. This is complicated for a number of different reasons, but essentially calculating minimum eigenvalues is somehow an unstable procedure. We need a floating point safe or a floating point sensitive, since it would abound for the floating point sensitivity on the calculation of this minimum eigenvalue. But the error in this calculation implicitly depends on the condition number of the matrix. So you kind of get this chicken and egg problem where we don't know the condition number, so we can't estimate this thing well, and it's hard to implement privately as a result, or in a floating point safe manner as a result. So it's unclear how we could actually control the error in this optimal part of the optimization process, which means it's hard to understand how we could actually make this whole thing floating point safe. So given all this, I do want to talk last.
I had a question.
Yeah.
I have a question, but it might be a dumb question. When you said that the eigenvalue is determined by what I assume is like the count of rows in the data set to some degree, and you don't know what that count is, what happens if you use a noisy count that is like close but slightly off? Does it just break the eigenvalue calculation entirely, or can that be done?
I think any calculation, you would really need to know the number of rows in the data set. The reason for this is because any calculation to find the eigenvalue or find the minimum singular value of a matrix would implicitly require doing things like involving this matrix in like some matrix iteration or something like that. And unless I'm mistaken, I feel like that would require knowledge, like exact knowledge of what the number of rows in your data set would be.
Got it. Okay, yeah.
But if the number of rows is the number of like people's data, like isn't like X transpose X like isn't it like it's like D by D, not N by N, or maybe
Would the matrix iteration for solving this kind of problem not look something like I'm blanking on how the procedures work, but you do something like multiply X by I see your point.
Crestron. Amal.
Yeah.
I think Crestron will put Walt on the room.
Oh, okay.
Crestron. You go.
No, I mean like because it's not coming out of the owl for some reason, but it's not showing up here
Okay,
either.
try Crestron, then maybe that Walt will be on the room speaker. Try that and see if that works.
I'm sorry.
It was there in the same.
Oh, okay.
The second bucket
Speaker.
Speaker. Okay.
Crestron.
Oh, same. Oh, Crestron. Okay.
Or you can try that.
Isn't it?
This is. I don't know
What? Should I?
All right, let's solve it. Worry about it.
Okay. I think to Walt's point, that thank you for pointing that out, Walt. There may be ways to get around it.
Check, make sure that recording is still on. Yeah, it's recording.
Okay. Am I good to keep going? I think we're still recording, and
Yeah, it's still recording.
it's harder than anything we're doing here. So the last part of stuff that I'm going to talk about today is related to the empirical performance of all these algorithms. So first, just to make sure that we're all on the same page in terms of these experiments, the first setting I'm going to talk about is going to involve IID Gaussian data or synthetic data. I know that's kind of a hot word these days, but it's not like that kind of synthetic data. So I'll fix some parameter norm or some true parameter. I'll generate data via this like fairly standard data generation process, and I'll vary the covariate and label clipping norm R, as well as the norm of my covariates. And I'll use this to show, at least synthetically, that there are examples of covariate distributions that can't really be handled well by either Noisy-SGD or by AdaSSP. In terms of real-world data, I showcase a subset of the UCI regression data sets. I think the details of them aren't super important, but we do clip covariates and labels jointly at R equals 1. And this is sometimes okay and sometimes not. So to talk first about mostly nice Gaussian data, we find that basically when the I think I have a thing that's cut off there. You might close that. Yeah, thank you. Yeah. So when the data clipping range is appropriate or well chosen based on the synthetic data, as an example here, we use, I want to say R equals 2, and we're drawing from an isotropic Gaussian. All of these algorithms are going to perform reasonably well. That is, by the time we get a sufficiently large sample size, we'll converge to a prediction MST that's like below 10 to the power of -1 or something. That said, DP-SGD typically has the best performance here, even when the data is ill-conditioned, although the ill-conditioning introduces some additional error or some additional hardness into the optimization problem. And we see that this surfaces as a gap between the non-private and the private solution, even as the sample size becomes large enough for convergence to the non-private solution for other algorithms like AdaSSP, as an example. But by and large, DP-SGD, even in this like standard Gaussian case, is like still better than some of the other algorithms that we talked about.
Sorry, can you remind me what ill-conditioned is?
So ill-conditioned means that the covariates are like very skewed, something like that. So the ratio between like the largest direction of my data's covariates and the smallest direction, in this case, would be about 100 in terms of norm. Does that? And when we take a look at Gaussians, where the covariates are very far away from the origin, and the clipping bias is significant, we can actually see that DP-SGD converges at a pretty small sample size. And curiously, we have even worse, in fact, basically useless performance for Noisy-SGD at pretty much all sample sizes. And with AdaSSP, we see a meaningful gap between DP-SGD and AdaSSP, even as the sample size becomes much larger. Consequently, we conclude that when the data clipping range is going to introduce bias, as in the left side, so we clip at R equals 1, while our covariates are very far away from the origin, in fact, about 100 units of magnitude on a dimension, if I want to say 100. And on the right, when we take the radius to be sufficiently large to include most of these covariates, the additional error that's introduced by our choice of doing this, because our utility guarantees our privacy guarantees depend on the choice of radius, DP-SGD still has the best performance. And we see that the trade-offs are a little worse than they were in the case where the data was nice and sufficient for this optimization case. In terms of real-world data, we see a pretty similar story. On real-world data that's somehow friendly to clipping and to normalization, we see that Noisy-SGD and AdaSSP have somewhat similar, at times better than, at times worse than, performance relative to DP-SGD. Sometimes there are cases where DP-SGD's hyperparameters are just chosen in a not helpful way, and to avoid incurring additional privacy loss, we can't really tune these parameters. So we see, for example, on the right, DP-SGD doesn't really converge or do anything as a function of the privacy parameter, which to us indicates that not much is happening, and DP-SGD is in fact not convergent. But we still see that in cases where the data is somehow either ill-conditioned or the data's norm is very far away from the origin, where these clipping biases introduce real statistical error, we still see that DP-SGD can improve considerably over other algorithms. In all three of these cases, DP-SGD either reaches or beats the non-private error. This is possible because sometimes DP-SGD has some implicit bias that can improve the generalization error, although the reasons for this are possibly outside of the scope of this talk. And in general, beat other algorithms by orders of magnitude, or only match other algorithms when the privacy parameter becomes large. So altogether, given all this, we've studied the trade-offs of private linear regression algorithms. We showed that between composition and masked iterate, they're mostly the same in all of the regimes we cared about. We discussed some challenges with implementing AdaSSP and Noisy-SGD in a floating point safe manner, and showed that DP-SGD is actually not too hard to implement safely. And finally, we experimentally showed that DP-SGD performs quite well under this set of minimal assumptions, specifically referring to bounded parameter norm and bounded data norm. As a result of all this experimentation, we're pretty close to shipping a floating point safe implementation of DP-SGD for linear problems in the library, which I think is pretty cool, and I hope will be a cool addition to the library in the coming few weeks. Some future work that I did want to mention is that we should probably explore the viability of some other private regression algorithms that maybe have fewer drawbacks. Things like, for example, iterative Hessian mixing by some folks at, I think, MIT and the University of Jerusalem, and two-key regression, which is a pretty cool paper that doesn't require any hyperparameter tuning at all. Another direction that I think would be great would be to understand and implement floating point safe private hyperparameter selection algorithms to automate the process of choosing a good learning rate and other hyperparameters for DP-SGD, since that's really the only moving part that we have to choose. Yeah, so that's everything I have to say technically. Otherwise, I really want to thank you guys for the opportunity to work with OpenDP. I care about privacy a lot. It's kind of been a dream come true. I think I said this at the start of the summer, but I want to say it again. I have some folks I want to thank in particular. Thanks to Swil for starting OpenDP. Obviously, it wouldn't be here if that wasn't a thing. I want to thank Walt for all of the really cool mentorship. I learned a ton this summer, and I think a lot of it is because Walt was willing to sit with me for like an hour and a half and 2 hours and argue about problems, and that's nice and cool. I also want to thank Mike, Eddie, and Chuck for all of the mentorship that you guys have provided in different ways, informal conversations and different things. I guess I don't have it on the slide, but I also really want to thank Mike and Alice for their great work on the continuous Gaussian sampler, which actually enables the floating point safety of everything that I've done this summer. So that's pretty cool. Thanks, guys. And Amal for putting all this awesome work into organizing the summer program. Yeah. Super cool to be here. Let me know if you have any questions.
One quick question.
Yeah.
On the UCI data sets, did you look at the difference in how quickly DP-SGD converged to the non-private performance based on how good of a classifier was in the first place, or prediction algorithm?
So the examples that I have here are typically examples where the non-private classifier has like reasonable performance.
Like they're all pretty similar performance?
No.
Because I was imagining, you could have like one data set where your non-private prediction algorithm is way better, and then another data set where it's like really bad. And I'm curious, like, do you converge quickly when it's bad just because like the non-private one was bad already?
When it's bad, I think the story is more complicated. Okay. But I will say that if it's hard to do linear regression when it's non-private, it's probably a lot harder to do it when it is private. So although I didn't present those examples today, I think from having looked at the data, I would say that like they can vary a lot. There are examples where the non-private regression parameter is bad and DP-SGD might do a little better due to this implicit bias thing, but not meaningfully enough to make it a useful predictor. It's possible that the best predictor is just not a very good predictor.
So you don't think that it's necessarily correlated to the performance of the non-private?
No.
Interesting.
Maybe there's something like more nuanced you could say. It's not clear to me what it is, but I think it would be an interesting avenue for exploration.
So, if there are more questions, we could jump to.
Yeah, I think maybe because of time, we'll have more discussion over lunch.
Yeah. All right. So